This is Mr. Beck Does Your Homework. Homework AP Physics 8.3, questions 7 and 8. 2 moles of an ideal gas, initially at temperature 22 Celsius, undergoes an expansion at a constant pressure of 1 atmosphere to 2 times its original volume. What is the new temperature of the gas? The universal gas constant is blah, blah, blah. Okay, so what I have, the first way to think about this is you could do a Pivnert problem. Because you know the 2 moles, so you know N equals 2 moles. The pressure is 1 atmosphere, so my pressure is 1 atmosphere, which you can convert to kilopascals. So that's going to be, or sorry, pascals. That's 101,300 pascals. To 2 times its original volume. That means I don't know my original volume. But I do know that my initial temperature, initially at a temperature of 22 Celsius, so my temperature is 22 degrees Celsius. If I add 273, I will get my Kelvin temperature. Okay, so that'll give me kelvins. So it's asking for the new temperature of the gas. So the straightforward way of doing this is to do Pivnert, solve for volume, because you know pressure, number of moles, universal gas constant is 8.31, and temperature. So you know everything but V, so you can solve for V. Then you can double V and plug it back in. Now you know P and V and N and R, and you'll be looking for T. So this would be a very straightforward way of doing this, and it would take you a lot of time. The other thing you could do is recognize that PV equals nRT. Well, I know that N is going to be constant. I know that R is going to be a constant, as it always is. And I know that my pressure is going to be held constant of 1 atmosphere. So this tells me that my volume divided by my temperature is going to be N times R over P, all of which are constant. So since volume over temperature is constant, then I know that V1 over T1 is going to equal V2 over T2. And if my new volume is twice my original volume, then V2 is going to be twice V1, so T2 has to be twice T1. So once you get your Kelvin temperature, double it, and you will get your new temperature. So in order to make the volume double, my temperature has to be double if everything else stays the same. So this is the straightforward way of doing it, to do Pivnert, solve for volume, double the volume, solve for your new temperature, or you can just simply do it this way. So twice my temperature is my old temperature. Now for the tricky part, find the work done on the gas during the expansion. So I've got 2 things here. I could figure out that I know that my work done on the gas is going to be negative of the pressure times the change in the volume, because this gas is expanding. So I am taking the gas, I'm letting it expand. As I let the gas expand, I'm doing negative work because I'm pushing that way and the gas is expanding that way, so the volume is increasing. So I'm doing negative work because my force is opposite the direction of motion of that piston. So that's why it's pressure times change in volume, because this is also force times distance gives me pressure times change in volume. Now, I know the pressure, that's 1 atmosphere or 101,300 pascals. I don't know my change in volume. So again, here, you could calculate your initial volume using PV equals nRT. You could calculate your final volume using PV equals nRT. Now you've got your delta V, plug in the P, and you've got yourself work done. Another way of doing it, which involves a little bit of algebra, if you think work is P delta V, and you've got PV equals nRT, so let's take this work equals negative P delta V. Well, delta V is going to be my V2 minus V1. So my work is going to be negative of my pressure times V2 minus V1. So my work is going to be negative of PV2 minus PV1. But PV equals nRT. So I know that my work is going to be negative nRT2 minus nRT1. Now I can pull out some of my like terms here. So I know that N can be pulled out. So my work is going to be negative of N times R times T2 minus T1. And since you know your original temperature and you know your new temperature, because that's what you solved for here. Oh, this is answer in units of Celsius, so don't forget to, once you've doubled this Kelvin, subtract 273 from it again. So that's back to number 7. Sorry, number 7. Okay. So now it's nR times T2 minus T1. This could be Kelvin or Celsius, it doesn't matter, but you've got your temperature and you've doubled it. So your T2 minus T1 is actually going to be this original Kelvin temperature here, because if you take it and you double it and then you subtract the original. So this is actually going to be negative of N, which is number of moles, which is 2, times R, which is 8.31, times my original Kelvin temperature, which is this number. And that's going to be the work done on the gas. But that'll be in joules. This asks for kilojoules. So take that and divide by 1,000, and that's going to give you joules. Isn't that cool?